question 6 start off by asking you this fixed essay. So there are quite a lot of these kind of fixed essay question. This is a 4-mark fixed essay, so you gotta be prepared for this kind of thing and scenario. They want you from the most acidic to the least acidic, so we gotta try and think about these things and compare them one by one. Butanoic acid is a 4-carbon carboxylic acid, and we have ethanol. Ethanol is 2-carbon alcohol, and we have ethanoic acid, a 2-carbon carboxylic acid. I don't know why my carboxylic acid is not drawn very well, but anyway. And I have water. Water is just H2O there. Okay, the first thing I can say in my essay is I don't want to write down the answer first. Okay, so these are the given one. I really don't want, I'm not saying that, these are from most acidic to least acidic, so I leave a question mark there. Okay, so the first thing in my essay is I would say the more stable the conjugate base, the more stable the conjugate base. Conjugate base is the species you get after the acid donates the proton. So the more stable the conjugate base, the more acidic is the substance. The more acidic is the substance. So which one can I compare first? Out of all these three, out of all these four, I think I can compare the carboxylic acid first. Carboxylic acid are most acidic as the carboxylate. The carboxylate, the negative charge on the carboxylate can be delocalized through the CO pi system. I'm just going to demonstrate it now. So example, when you have CO minus like this, and then you can donate that and give you this resonance structure, this alternative structure, so you can delocalize these electrons, not just on this oxygen, but also delocalize it over the carbonium, and you can get two equal structure there. I've just shown an example there. It's the same thing for this butanoate, but our question really is, among the carboxylic acid, which one is going to be more acidic? Now, when you have a butanoic acid versus ethanoic acid, so we are comparing this thing versus this. So this is a 1, 2, 3, 4. This is a 1 and 2. Which one is going to be more stable? This is a CH3 group that donates to that ethanoate, and this is a CH3 CH2 CH2 that donates to this. So you can think about the electron donating effect. So in terms of the electron donating effect by inductive effect, so these are straight from the topic on inductive effect and electron donating groups of the alkyls from the stability of carbocation. Here we have a negative charge. More electron donating means you will destabilize the negative charge. So therefore, more electron donating, CH3, CH2, CH2 compared to CH3 means destabilize, means destabilizes. It means it destabilizes the conjugate base more. Destabilizes the former or the previous, the conjugate base destabilizes that thing there, 1, 2, 3, 4, or minus more. Therefore, this thing is a weaker acid than ethanoic acid. Okay, so we got our first trend there, and this effect there is called inductive electron donating effect. Yeah, inductive electron donating effect of the alkyl groups. Onto the carboxylic acid. Well, carboxylic acid is definitely more acidic than the water because it's a more acidic group compared to the other one. Onto alcohol and water. So if we look at alcohol versus water, so if I have alcohol, then this is the conjugate base versus H minus. Now we can see that the alkyl electron donating group on the alkox side, or I can say etox side, meaning CH3, CH2, or minus. Okay, by inductive effect, will destabilize the conjugate base more than just the hydrogen does for OH minus. Because the hydrogen just, it just forms a covalent bond. They don't do that donation of electrons because oxygen is naturally electron negative to begin with. Therefore, we can say that we can say that the alcohol CH3 CH2OH is going to be less acidic than water. So now I am ready to state from the most acidic to the least acidic. So the most acidic is going to be, if you compare the carboxylic acid, this is weaker than this. So this is going to be the stronger acid. So you start from ethanoic acid. And then you follow that by butanoic acid, as I've explained why butanoic acid is a weaker acid than ethanoic acid. And then between water and also the ethanol, we compare the stability of the conjugate base. This is more destabilized, so this is going to be more stable compared to this. So this is going to be giving us water as being more acidic compared to the ethanol. So ethanol is the least acidic after all because the conjugate base is the most destabilized. As a result of that, at least here you might think the electron donating group destabilizes the negative charge. It does to some extent, but you remember you can also delocalize over the carbon-oxygen carbonyl pi system. That's why carboxylic acid is always going to be more acidic than either of these two there. So that's the end of that 4 marks essay question. On to part B. So this is question 6, part B. These are a bunch of tests. So some of them you get observed results, some of them you don't get observed results. And you're supposed to complete the table with the reagents and conditions for a positive test. So we have test number 1, and we have reagents, and we also need to write down the conditions as well. So I don't want to copy down the whole entire table, but I might have to actually. So CO2H, and then I think I'll just draw the skeletal formula because it's a lot easier based on what I will do in a little bit anyway. So there's methanoic acid, and then that is going to be ethane-dioic acid, and the next one is propane-dioic acid, I think. CH3, CH2, no, sorry, butane-dioic acid. And then what is going to be observed change? I'm running out of space here. So what is going to be your change? Your observation. Observe change. So let me see if I can come up with this table very, very nicely. One of the perks of doing it on screen is I get to do all this without having to, worry about how neat I am. So yeah, let's try a different color. So test 1. So they said this is positive, this is negative, and negative. So what can react with methanoic acid? So methanoic acid is a case study in AS, whereas ethane-dioic acid is a case study in A2 under carboxylic acid. So make sure you know these because they can ask you anything from AS in A2. So ethane-dioic acid and this butane-dioic acid cannot undergo this reaction, but this one can because you have one hydrogen there. So it looks like an aldehyde on this end. That is why methanoic acid can be oxidized by Fellings and also by Tollens reagent. So what I can say is you can use things like oxidizing agent, but you cannot use KMnO4 because this can also react with KMnO4. So you want to avoid KMnO4, but what you can do is you can use Fellings or tolerance reagent because this group there looks like aldehyde. So you can use Fellings, for example. So Fellings reagent, and Fellings reagent you need to warm it as well together with this methanoic acid. And Fellings reagent is a solution of copper 2 plus to begin with. What you will get is you will get a brick red PPT, brick red precipitate, as a result of copper 1 oxide forming. After the methanoic acid there gets oxidized, the Fellings reagent get reduced from copper plus 2 to copper plus 1. Okay, on to the second test. What we have is, let's have a look at the tick and the crosses. So this reacts and this reacts, but this doesn't react. So these are just normal carboxylic acid. This ethane dioic acid can be further oxidized, but under extreme oxidation condition. So you need a very strong oxidizing agent, which is H plus and KMnO4, or you can write MnO4 minus. It's entirely up to you, but whatever you do, you must have the acid, otherwise there's no reaction, and you need to reflux this. Okay, so what happens is the methanoic acid can be oxidized completely to give you CO2 and H2O. This will be oxidized completely to give you CO2 and H2O. So what you will get is you don't see the H2O and CO2. Instead, you see the purple KMnO4 aqueous. The solution gets decolorized, or you go from purple to colorless because the manganese plus 7 go to manganese 2 plus, which is manganese plus 2, and that is no longer the intensely purple color, from purple to kind of colorless or very pale pink. That's why you see these color changes. And assume these organic acids all have similar acid strength. Yep, that's all right, I guess. So that's it for the 3 marks. We now have the next part of the question where they want us to think about proton NMR. So this is B part 2. So number of peaks in the proton NMR. If I just copy down the structure, because I can't be bothered to draw them again and again. So copy and paste them. Okay, but what I don't want is I don't need the line there. I don't need this. I can just move that a little bit apart so I have some space there. Okay, so let's have a look at the number of different proton environments. So they want the number of peaks in proton NMR. So the number of, well, basically proton NMR and then carbon NMR as well. Whew, okay, so they got this the other way around, which is okay. And that, which is okay as well. So if I have that particular table there, I could have proton NMR, how many peak, and then carbon 13 NMR, how many peaks. Alright, so carbon, let's do carbon first. Carbon means look for the number of different carbon. I just have 1 carbon there, so just 1 peak. I have 1 carbon and 2 carbon, but if you think about it, it's symmetrical. It's symmetrical, meaning both carbons are the exact same environment. So this carbon is exactly the same as that carbon. I still get 1 environment. Here, you're also looking at symmetry, which is symmetrical about the 2 carbons. But this is a carboxylic acid carbon, whereas you also get another carbon, which is a CH2 carbon. So these and these are the same. And then the red one, the red one and the red one are exactly the same. So altogether, you just get 2 carbon environment. How about proton environment? Proton environment, you got 1 proton, which is like aldehyde proton there, and then 1 for the carboxylic acid. So you got 2 proton environment, 1 there and 1 there. You only have 1 proton environment here because there's no proton on this carbon from 4 bond. So you can have a look at the structural formula and you can see it. I've just converted this to skeletal formula because for me, skeletal formula is the easiest and the most elegant way to see through this thing. This proton is the same as that proton. By symmetry, there's only 1 proton environment there. Now to the proton for the last one. So this proton that I've underlined in green, they are exactly the same. And this proton there, which I'm going to show you there, so 2H there, is going to be the same as this 2H there. So altogether, you just have 1 proton environment and 2 proton environment because this and this will appear the same place and this will appear in the same place. So that's it really, filling in the blanks in terms of how many different proton environment, how many carbon environment are there. On to the next part, which is to do with fast exchange. So they are saying that when you have this carboxylic acid, which is metanoic acid, and you have like that. Actually, why am I drawing display? They said that in D2O, then you can, what would it look differently if you compare the proton NMR here, which is two proton environments, compared to in D2O. In D2O, what can happen is I can write this equation, and in fact it's better if I write structural formula. So HCO2H, then what happens is the H on the end there will remain, but the CO2 can change the OH of the carboxylic acid with the deuterium of the D2O. So I get HOD. Deuterium is just heavy isotope of hydrogen. It's still the exact same thing. It's just no longer hydrogen. Here you have two proton environment, one there, which is no longer there, which is now which is now lost and part of the water now. Your molecule still have the hydrogen underlying in green there. So what happened is, this is what you call fast exchange. You can write an equation to show it. So as your reason number 1. So describe and explain. So this is your explanation. So the HCO2H undergoes fast exchange with D2O. The OH it's no longer present. Therefore, the peak due to OH disappears. Now only one peak in the proton NMR after this fast exchange. Previously you have two peaks as you have done in your table, one there and one for this hydrogen there. Now you have lost this peak as a result of fast exchange. It's no longer with a hydrogen, it's no longer with a proton, but now it's now with a deuterium, which is NMR inactive. Okay, that's the idea of fast exchange there. So on to the next part of the question. So this is still question 6. Question 6, part C. We have 1,4-dibromobutane. If I just convert that to skeletal formula, because you know how much I like skeletal formula. So there's 1,4-dibromobutane. And looking at that, this is a synthesis. So I get G, I get H. It seems like I need to work backward because they have given us the end product, which is J. And J is this HO, carboxylic acid, and then CH2, and then carboxylic acid. So this is 1, 2, 3, and 4. The next one is K. So this is H2N. So it's an amine. If you count the carbon there, 1, 2, 3, 4, 5, 6. So it's a 6 carbon. So 1, 2, 3, 4, 5, 6, and then NH2. Let's count again, because whatever you do, you always check. You count the carbon, CH2, there are 6 of them. CH2, 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 blah, blah, blah. NH2 at the end. This is a diamine. So these things are what you call amine. So this is a diamine. This is a 1,6-hexadiamine. 1,6-hexadiamine. I think I got this the other way around. 1,6-diamine. That sounds more correct. Okay. Anyway, this next one is butane 1,4-dioic acid. That was given in the previous question anyway. Butane 1,4-dioic acid. Let me check. Did I spell that correctly? Yep, there's butane dioic acid. So yeah, I mean there's step 2, there's step 4, and then that is step 1 to make G. There is step 3 to make H. Draw the structure of G and H. Okay, now if we look at these, there's 1, 2, 3, and 4 carbon, and I have 1, 2, 3, and 4 carbon there. So we can definitely see that there's the same number of carbon there, so there's no addition of carbon. But from the 4 carbon there, you can hopefully see that the original carbon there will be the middle the middle carbon there, because then you have additional carbon, one at the end there, carbon 1, and one at the carbon 6 there, which I've drawn in blue. Not too sure, I should have used a laser pointer to guide you here rather than just to use the highlighter to put it in just now. But anyway, so you have added carbon there, you've added a carbon there. So the idea really there is add carbon. No need to add carbon. Okay, so we should be able to go backward in terms of which step require adding carbon, which step require not adding carbon. So if I'm to draw the structure, they don't say draw skeletal or draw structural. I personally would just draw skeletal, okay, because well, you know me, I like skeletal. So that is just going to be butane 1,4-diol. That's just going to be G there. So that makes sense for G because we could just do hydrolysis. So this is going to be hydrolysis is the type of reaction where you're actually substituting the Br with the OH. And then what we can do with that OH at the end there is we could oxidize a primary alcohol to carboxylic acid. Primary alcohol because the carbon with the OH is bonded to one carbon. Primary alcohol because the carbon with the OH is bonded to one other carbon there. So this is just going to be oxidation of primary alcohol there. On the other hand, for H, we have seen that we need to add carbon. So this has to be done using nitrile. So there's C triple bond N, there's C triple bond N. So let me just get this straight. 1, 2, nope, I have done this incorrectly. Carbon 1 is still carbon 1 there. So it is carbon 1 that is bonded to a new carbon there, which is C triple bond N. It is carbon 4 that is now bonded to a new carbon. There's now triple bond N. So even if you want to draw skeletal formula, make sure that you are drawing the right stuff and not just randomly drawing without checking. So that is one of the biggest mistakes you can ever make, drawing without checking. So now I have 1, 2, 3, 4, which are the one in red. So obviously you don't use highlighter in the real exam, but I'm just showing you that the one in red and now the one in blue comes from this C triple bond N and C triple bond N. And that reaction there will be hydrolysis. So it's going to be the acid, oops, sorry, not acid. It has to be base hydrolysis. Am I correct? Nope, it's not hydrolysis at all because hydrolysis would give you carboxylic acid. You want amine. So this is going to be reduction. You need to have reduction of the nitrile, then you can get amine. Cannot be hydrolysis because then you get carboxylic acid. From here to here, that is definitely a substitution. The mechanism is called nucleophilic substitution, but the type of reaction is just substitution there. Okay, so I've done the structure of G and H. Now we need to think about reagent and condition for each of these steps. So step one is hydrolysis. I would need NaOH aqueous because it is done in water. That's why it's hydrolysis. Then the condition, I will also need reflux for step 1. For step 2, this is the oxidation of primary alcohol. So I would need H plus and Cr2 or 7,2-. This is called acidified dichromate 6. And I also need a reflux condition. For step 3, nucleophilic substitution with Cn-. So what I need is KCN or NaCN in ethanol. And I would need to reflux this reaction mixture. Okay. For reaction 4, this is reduction of nitrile to amine. So step 4, reduction of the nitrile to amine, I need lithium aluminium hydride, and this is to be used in dry ether as lithium aluminium hydride is very sensitive to water. So we always use it in dry ether, and we can reflux this as well. Okay, so altogether, I will just copy paste each of these now so that they are neat and tidy at the bottom there. I don't want that box there. Step 2, I'm just putting them all in one place now so that it's easy for me to find it and retrieve this file later on if I have to share with a student in the future. Of course, I am not sharing these online randomly. So I do offer private tutoring as well, so it's $40 an hour. If you think about whether it's worth it or not, I can assure you it is definitely worth it given my expertise, given what you can learn from me on a one-to-one tutoring. Anyway, so those are the reagents and conditions for each of the steps that I have outlined previously. Going to the last part of this question is actually about polymerization for 2 marks. They say you can get polyamide, so polyamide L, and you get it from J, which is the carboxylic acid, HCO2H there, and you get CH2, CH2, and then CO2H, and then you have K, which is the diamine. So you're gonna form 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, and then NH2, 1, 2, 3, 4, 5, 6. Okay, so this is your diamine. Oops, sorry. This is your diamine. This is your dicarboxylic acid. You want a polyamide. So you got to think about what will the OH lose. The OH will lose the, the carboxylic acid will lose the OH. And then what would the amine lose? The amine will also, it will lose the H only. So ultimately, what you get is, you get the polymer. They want you to fully display the functional group. In the question, they say fully display any functional group. So the functional group that you're going to get is the amide. Amide functional group is going to be C double bond O and H, like that. Even the O level or the IGCSE level education will have taught you that. So be very careful about that. So there's carbon O, and then there's your NH, and then there's your CH2, which I can just write, there are 6 of them. I think I should write using the simplified format to avoid writing so much. So there's CH2 there, because there's 2 CH2 as given in the question. And then of course that is also continuing to the C double bond O display there. There's the display of the amide unit, and the CH2 is also then combined to another NH, and that continues on and on. So this is polymer L, and I have fully displayed the amide unit. So that is going to be amide unit, and how many, or the amide linkage. They say draw the repeat unit. So this is the repeat unit, which consists of 2 different monomers, because each of the monomer has the dioic acid as well as the diamine group. So I need at least 2 of these monomer to condense together. This is a condensation polymer, because you are forming polyamide. This is condensation polymerization. Just like when you form ester or when you form amide, you kick out water. That's why we kick out the H and the OH there. We kick out water. It's a condensation reaction. So this is 1 repeat unit of this polyamide there. Fully display the amide unit. I have gotten the CH2 twice for the butane dioic acid there. I've gotten the CH2 6 times for the hexa 1,6 diamine there. And I think that's it for that 18 mark question number 6 there.